We're continuing on with part B of chapter 11 on the nervous system. Let me go ahead and blow this presentation up so you can see it larger. This is a really good illustration of the resting membrane potential. And I'll try to explain it to you as best I can. But in the first, is at the top, in the first picture at the top, what you have is nothing but these purple channels are channels that only allow potassium through. And then what's not on here is those large negatively charged proteins that are inside the cell interior. And there's none of those on the outside. They're all inside the cell and they can't get out. They're too large, okay? So these negatively charged proteins and just a few potassium leakage channels allowing some potassium out would keep the cell interior at -90. Now let's throw in a sodium leak channel. Sodium has a positive charge. So if we have just, and we've already talked about that there's 25 times more potassium leak channels in the plasma membrane than there are sodium. But even if there's just a few, the amount of sodium that leaks in, because it flows from its high concentration to its low concentration, causes the cell interior to go up to -70. So without the sodium leak channels, we have -90 millivolts. When you put the sodium leak channels in there, the leakage of those positively charged sodium ions brings the potential up to -70. So it's going to be less negative than what it was. It's not positive yet, but it's less negative. -70 is less negative than -90. Okay? Now let's put the sodium-potassium pump in there. Now, the sodium-potassium pump, because there's so much permeability already to potassium, it's just going to pump a little bit of potassium into the cell, just 2 for every 3 sodiums that it pumps out. And that maintains the voltage at -70. Pumping more positive out than in maintains the voltage at -70. It kind of all interacts with the fact that the cell is more permeable to potassium, so more potassium is leaking out anyway, and it's less permeable to sodium, so less sodium is leaking in than potassium leaking out. So it compensates for that. All right, now the big thing is in the nervous system, we need the resting membrane potential to change. We need it to change either to a graded potential or an action potential. We need it to change from -70 to a more positive value if we want it to lead to an action potential. Okay, so a graded potential, you can have a graded potential on the dendrites or the cell body. These signals can summate, they can add up to produce a larger change in voltage across the plasma membrane. But the only way you're going to get an action potential, which can only be transmitted down an action axon, is if the graded potential is large enough. If summating all of the potentials that arrive at the dendrites and cell body, if that value is large enough, then an action potential can be generated. Okay? When we use the term depolarization, depolarization is going to happen in the cell whenever it becomes less negative than what it was. So if this is our plasma membrane and it's -70 right now, we have some chemical that comes along and causes our closed sodium channels to open. They were closed, now they're going to open. And not just one channel, but several channels, so a lot of sodium can come in. Sodium is going to come in real fast because it's already way more sodium on the outside than inside. So if sodium, which is positive, comes in, then the voltage is going to go like from -70 to -69 to, -60 and so on. It's going to become less negative, and it may even become positive. But depolarization just means that positive ions come into the cell and make the membrane potential less negative. Hyperpolarization means that potassium ions leave the cell and the membrane becomes more negative. So if we were to have a cell just like this one that was at -70, I'm just going to draw it up here. So we've got -70 millivolts already, and we have channels for potassium that allow positive ions to leak out. Then our -70 is going to become more and more negative because we're losing positive ions. So hyperpolarization is caused by potassium leaving the cell. Depolarization is caused by sodium entering the cell. And this is a little graph that kind of shows you depolarization means that -70 is going to become less negative. And again, that happens when positive ions come into the cell. Hyperpolarization means that the resting potential is going to become more negative, and that is when positive ions leave the cell. Graded potentials are short and they're localized. You only have graded potentials along the dendrites and the cell body. The way they work is this. One region of the plasma membrane is depolarized, and it can lead to depolarization, here and here and here, but at some point it's going to stop. If this were an action potential, that depolarization would travel all the way down the axon, all the way to the axon terminals. Okay, but this is going to be some sodium coming in, sodium's coming in, and we already talked about how that's going to make the membrane potential less negative or more positive. Okay. All right, so once the gated ion channel opens, depolarization spreads from one area to the next, and that's how the spreading of that depolarization creates local currents, which are represented by the black arrows that depolarize adjacent membrane areas. So depolarization can spread a little bit, but it's not going to go all the way. I mean, it's not like an action potential. It can be large or it can be small, but it does have a stopping point. Okay. Graded potentials, the thing about graded is they can be different numbers. An action potential, it's got to be +30. You've got to have a depolarization to +30. Well, you've got to have a depolarization to -55 to get an action potential. But the peak of the action potential is +30. The point is, unless you get depolarization to -55, if that graded potential does not change the voltage from -70 to -55, enough sodium ions don't come in to make this change, you will not get an action potential generated at the axon hillock and then travel down the axon. Okay, so graded potentials have values and they're over short, they have different values and they're over short distances. Okay, and with distance, the membrane potential decays. So the further that membrane potential, the further the spread of the graded potential, the less strength that it has. All right, now an action potential is also referred to as a nerve impulse. This is a long distance potential. The key players, it says, are voltage sodium gated channels and voltage potassium channels. In a resting state, all the gated sodium and potassium channels are closed. So the only way that these ions are getting in and out is through the sodium potassium pump and the leakage channels for potassium and the leakage channels for sodium. But there's only a certain amount, and everything kind of works together so that voltage stays at -70. Now, the voltage gated channels, if a sodium voltage gated channel opens, sodium comes into the cell, a lot of sodium comes into the cell. And then that -70 becomes less negative. And that is called depolarization. But the depolarization, enough sodium has to come in to reach somewhere between -55 to -50. That is called threshold. If threshold is reached at the axon hillock, the membrane polarity is going to jump to +30. Sodium is going to rush in, and it's going to cause the membrane polarity to become all the way as high as +30. That +30 is going to trigger potassium channels. And then the sodium channels will close and the potassium will come into the cell. The potassium will go out of the cell, and that will cause it to go back to its potential, its regular potential. So let's look at this entire picture. So here's what we have, the events of an action potential. What we have is resting membrane potential. The sodium gate is opened. So something causes that sodium gate to open. Now sodium comes in, and we're going to get depolarization, which means that the -70 is going to become less negative. Okay? If depolarization reaches -55, if enough sodium comes in and that graded potential reaches the axon hillock, this is going to represent the axon hillock right here, and that graded potential reaches -55 at the axon hillock, then the action potential will happen. It's an all or nothing thing. If you get to -5 at the axon hillock, you're going to immediately have a +30 and then come back down to resting. Okay, so what causes the change from -70 to +30 is sodium ions coming in. But when that +30 gets here, those sodium gates inactivate. So sodium can't come in anymore. And the potassium gates open. So now our membrane is going to become more negative because it's losing positive ions. You kick the positive ions out, the membrane potential is going to go more negative. Okay, so now this is representing a closed sodium channel. When the ball is there, it's inactivated, but when this channel is closed because it has this gate that's closed, making it closed right there. Okay, so the reason there's a hyperpolarization during the action potential is because potassium channels are slow to close. So for a brief period of time, the potential goes from, say, -70 down to, I don't know, -80 or 90. And then the sodium potassium pump brings it back up to -70, which is resting membrane potential.